Welcome back to the last 10 days of logic here with Carneades.org and the 100 days of logic. Today we are doing day number 99. We're almost there. This day we are going to be looking at some final logic problems for you to solve. Now, in this video, we're just going to present the problems, and then over the course of the next couple of days, we're going to give you the answers to these problems. I've separated the problems out into kind of a beginner level, an intermediate level, and an expert level of problems. Let's take a look. So, the beginner level of problems. These are just propositional logic problems. If you only have the 18 rules of inference and conditional and indirect proof, you can do these problems. You could have done these problems after the first 45 days or so of the 100 days of logic. They're kind of just to get you back in the mode of doing logic problems. They shouldn't be that hard if you're already comfortable with things like predicate calculus. Or if you're having trouble with predicate calculus, these are going to be really good to build up kind of your basic skills so that you can go into those problems with more confidence. First one is P implies Q and R implies S. It's not the case that Q and S, therefore, it's not the case that P and R. The next one is P implies Q, R implies Q, therefore, P or R implies Q. These first two problems, I strongly encourage you to do these with only the 18 rules of inference. You don't even need conditional or indirect proof in order to solve these problems. Number 3, P implies Q. P implies Q implies R. Q implies R implies H. Therefore, P implies H. These next three, I'd encourage you to use conditional and indirect proof to solve them. You probably can solve them with the 18 rules of inference, and I'd be impressed if you did. But you can help yourself to conditional and indirect proof so you can get back into the mode of using that. Number 4, P or Q implies R and S. S or T implies U. P or T, therefore, U. A little bit trickier. And number 5, we just have a conclusion, which means this is a truth of logic. So you can use conditional and indirect proof to prove it, to get kind of premises to start working with for this. But it's going to be a truth of logic. So since it's true in all possible worlds, you should be able to prove it from without any premises. It is P, if and only if, P or Q and not Q. Give those a try. Those will be the first set of problems we will be looking at the answers to tomorrow. Next up, we have our intermediate level set of problems. These are problems for people who kind of have a good sense of predicate calculus, maybe not the more complicated parts of predicate calculus, but the basics of predicate calculus. That's using instantiation, generalization, change of quantifier, and conditional and indirect proof. If you have a good sense of that, these are great problems for you, and they'll really help you out getting to the more complicated problems in predicate calculus. So, first we have, for all x, x is an A implies x is a B or x is a C. G is an A, and it's not the case that G is a B. Therefore, G is a C. Problem number 1. Problem 2, there exists an x such that x is an A implies that for all x, x is a B. There exists an x such that x is a C implies that there exists an x such that x is a D. N is an A and N is a C. Therefore, there exists an x such that x is a B and x is a D. For these first two problems, I'd encourage you to try to solve them using only the rules of instantiation and generalization. Don't worry about using change of quantifier, conditional, and indirect proof. You can solve these problems with only those first 4 rules we learned in, I want to say, the second or third video in the last 10 days of logic. Problem number 3, there exists an x such that x is an A, or there exists an x such that x is a B and x is a C. It's not the case that there exists an x such that x is a B. Therefore, there exists an x such that x is an A. This problem and the next problem, you won't need conditional and indirect proof yet, but you should use change of quantifier. You're going to have a lot of trouble if you don't. Number 4, for all x, x is an a, and it's not the case that x is a b, implies that there exists some x such that x is a c. It's not the case that there exists an x such that x is a c or x is a b. Therefore, it's not the case that for all x, x is an a. Either of those, I encourage you to use change of quantifier with, and the last two, go ahead and use all of those rules as well as conditional and indirect proof. That's going to be for all x, x is an a implies x is a c. There exists an x such that x is a c implies there exists an x such that x is a b and x is a d. Therefore, there exists an x such that x is an a implies there exists an x such that x is a b. And problem number 6, for all x, x is a b implies x is a c and x is a d. Therefore, for all x, x is an a implies x is a b implies for all x, x is an a implies x is a d. Wow. Like I said, those are a little bit more middle of the road, intermediate. They're definitely tougher than the last set of problems, but they're not at the expert level. They're not really, really complicated or using some of the things that we've just more recently learned about. The expert problems we're going to be using, the more recent thing we've learned about, such as relations and overlapping quantifiers, identity, and modal logic. The first two problems are just covering relations and overlapping quantifiers. These will be: there exists an x such that for all y, y bears relation a to x, or for all x for all y, x bears relation b to y. Premise 2, there exists an x such that for all y, y is a c implies that it's not the case that y bears relation b to x. And we can conclude, for all x there exists a y such that x is a c implies x bears relation a to y. Getting a little more complicated. Problem 2. For all x, x is an I implies there exists an x such that x is a c and x is an a implies x is an e. There exists an x such that x is a t, or there exists an x such that x is a w implies there exists an x such that x is an I, and there exists an x such that x is a c. Premise 3, for all x, x is a c implies x is an a, and we conclude that there exists an x such that x is a t implies that there exists an x such that x is an I, and x is an e. Feel free to use conditional proof, any of the 18 rules of inference, instantiation, generalization, change of quantifier, anything at your disposal to solve these problems. Your rules about identity and your rules about modal logic aren't going to be really helpful here because there's no identity signs and there's no modal logic necessity and possibility. The next couple problems, we're going to do something a little bit different. They are what would seem to be needlessly complicated in the way they're written out in logical form. So I'm going to show you the kind of simplified actual version of these problems in word form, written out, to show you that sometimes it gets more complicated when you change them into symbolic form. Problem number 3. There are at least 2 apples in the tree. All apples are fruit. There are at most 2 fruit in the tree. Therefore, there are exactly 2 fruit in the tree. Seems like a fairly simple argument. However, whenever we get numerical quantities, that makes it pretty complicated. We can represent it with identity, but it gets a little tough. Here's how we would do it. There exists an x such that there exists a y, such that x is an apple and x is in the tree, and y is an apple and y is in the tree, and it's not the case that x is identical to y. That's there are at least 2 apples in the tree. All apples are fruit is for all x. X being an apple implies that x is a fruit. That one's pretty straightforward. There are at most 2 fruit in the tree. This is a little complicated. For all x, for all y, for all z, x being a fruit and x being in the tree, and y being a fruit and y being in the tree, and z being a fruit and z being in the tree implies that either x is identical to y, or y is identical to z, or x is identical to z. Basically, if there are 3 things that are fruit and in the tree, then at least 2 of those things are identical to each other. And finally, there exists an x such that there exists a y such that x is a fruit and x is in the tree, and y is a fruit and y is in the tree, and it's not the case that x is identical to y, and for all z is a fruit and z is in the tree implies that z is identical to x or z is identical to y. That's there are exactly 2 fruit in the tree. Kind of a combination of our first and third premise. Anyway, give that one a try. Use the premises and the conclusion and what you know about identity to see if you can prove the conclusion. We're going to do the same thing for number 4. We'll take the words, translate them into symbols, and then it'll be your job to take those symbols and go off and prove it. Premise 1. Every pet in the store was sold except for Joe and Fred. Premise 2. The only pet that was a tiger was Joe. Premise 3. Every pet was put up for adoption if and only if they were not a tiger and they were not sold. Premise 4. Fred is not Joe. Often you wouldn't see that premise in the actual original argument, but you could infer it from the fact that they seem to be 2 differently named people. If we were talking about Fred and Mr. Smith, we might not be able to infer that because Fred could be Mr. Smith, but usually if you have 2 different first names, we're probably talking about 2 different things. Therefore, exactly 1 pet was put up for adoption. Let's take a look at the translation. Joe is a pet and Fred is a pet, and it's not the case that Joe was sold, and it's not the case that Fred was sold, and for all x, if x is a pet and x is not Joe, and x is not Fred, that implies that x was sold. That's every pet was sold except for Joe and Fred. Premise 2, the only pet that was a tiger was Joe. That is, Joe is a tiger and Joe is a pet, and for all x being a pet and x being a tiger implies that x is Joe. Premise 3, every pet was put up for adoption if and only if they were not a tiger and they were not sold. That's going to be for all x is a pet implies that x was put up for adoption if and only if it's not the case that x is a tiger and it's not the case that x was sold. And finally, Fred is not Joe. It's not the case that Fred is Joe. Fairly simple there. And finally, the conclusion, therefore, exactly 1 pet was put up for adoption. There exists an x such that x is a pet and x is put up for adoption. And for all y is a pet and y is put up for adoption implies that y is identical to x. Give that one a try. See if you can prove the conclusion from the premises. Both of these last 2 problems are a little tough, but they're definitely not impossible, or they're definitely not excessively difficult. If you have learned all of the tricks that I've taught you in the identity video, you should be able to do both of these last problems. The final problems are going to be quite difficult. Let's take a look. Number 5. This, we're not going to translate it. We're not going to worry about that. This is just kind of an exercise in using all of the different things we learned in modal logic, a little bit from relations and overlapping quantifiers, and then some of the things we learned in the original series of videos. I'd strongly encourage you to look over the video on modal logic, I know it's a little long, before you tackle this problem as well as the next one, because that's really the key of what we're working with here. It's learning to use those tools of modal logic. You don't have to use even S4 or S5 at all to solve this problem, though. This is just going to be kind of those basic underlying rules that I taught you. The problem goes as follows. It's possible that there exists an x such that it's not the case that it's necessary that x is a d, or it's not the case that it's necessary that x is an e, implies for all x, there exists a y such that x is an a implies x bears relation b to y. Premise 2. There exists an x such that c bears relation b to x implies that it's not the case that it's possible that p is r and for all x, x is r. Premise 3, it's necessary that C is a D or C is an F, and C is an E or C is an F implies C is a Z. Therefore, C is an A implies C is a Z. It looks pretty complicated. It's definitely doable, and it's probably doable in fewer steps than the last couple of problems. It just uses those concepts in modal logic that may be a little bit harder to work with. Finally, problem number 6. What we're going to be doing is I'm going to be giving you the premises of the modal perfection argument and asking you to prove its conclusion. Now, you may disagree with the modal perfection argument because you don't agree with the premises. That doesn't mean that the argument isn't valid. It's a valid argument, and you can argue against the premises all you want, or you can argue against its use of S5, definitely. But you can't argue against the fact that once given those premises, the conclusion follows. If you don't know what the modal perfection argument is, check out my video on it where I give kind of a basic explanation and probably some hints towards proving this argument. What I'm going to do here is I'm going to give you the premises and ask you to prove the conclusion. We're going to kind of be introducing something of a new concept. It behaves exactly like concepts we've seen before, but that's going to be what makes this extremely challenging. So, first we'll start off with our definitions. P of F, this is our new concept. This is the idea that we can have predicates of predicates. That's what we're doing here. We're not saying that this is P of F and F is an object or an individual constant or a variable of a constant. It is actually a property. We're quantifying over a property. P of F, perfection F. P stands for perfection. It is better to have F than not. Gxy, x is greater than y. And x is s. S is supreme. And what that's going to translate out to in terms of the relation gxy is, it's not the case that it's possible that there exists a y such that y bears relation g to x, and it's not the case that it's possible that there exists a y such that it's not the case that x is identical to y, and it's not the case that x bears relation g to y. Next, we have our premises, the premises we're going to work off of. First premise is for all f, for all properties f, if f is a perfection, that implies that it's not the case that not f is a perfection. Premise 2, for all f, f is a perfection, implies that for all g, it's necessary that for all x, if x is an f, implies that x is a g, then g is a perfection. Premise 3, being supreme is a perfection. I cover translations of these in my video on the modal perfection argument. If you want to check that out, you can. And finally, the theorems. These are going to kind of be the additional rules of modal logic that we'll be using. It's possible that P and Q implies that it's possible that P and it's possible that Q. This is kind of a corollary of one of the M distribution theorems that I offered you before. It's nothing new, and it's not really anything controversial. T2, on the other hand, is a corollary of S5, so it's a little bit controversial itself. It's possible that it's not the case that it's possible that P implies it's not the case that it's possible that P. A corollary of S5 because we're reducing a dissimilar, a heterogeneous string of possibles and not possibles and necessary and not necessaries down to the last term in that sequence. It may seem like it might be S4 because we just have possibles, but because there's that not in there, and we remember we can actually change not possible over to necessary pretty easily just by using our change of modal quantifier rule, it's actually going to need S5 in order to do that. And finally, this is something I didn't introduce in the video on modal logic because it is controversial how you use normal, existential, and universal quantifiers with modal quantifiers like possibility and necessity, whether or not you can just pull a modal quantifier inside or outside of an existential quantifier. Quine doesn't even think it makes sense to have these two concepts in the same grouping. There's people that disagree with him, and there's people that have different versions of this. The rule that you'll need to use for the modal perfection argument goes as follows. It's possible that there exists an x such that x is f implies that there exists an x such that it's possible that x is f. Like I said, it's controversial. Finally, you'll be looking to conclude that there exists an x such that x is s, or x is supreme. It's pretty tough, and like I said, it uses kind of some new concepts that we haven't really played with, but I trust that you'll be able to do it if you look at it and work at it really hard. If you want some hints, you should check out the video on the modal perfection argument that's in my series of debunking the modal ontological argument 6 ways from Sunday, because that will give you some hints. It won't outline the whole argument step by step, but it'll give you some clues. All right? Whew! That was the last of the final logic problems. For the answers, we're going to be doling them out day by day. Tomorrow, we're going to be doing the beginner answers. Then the next day, we'll do the intermediate answers. Then the next day, we'll do the answers to the expert problems. And then finally, we will get to the 100th day of the 100 days of logic. Watch a new video every single day for 100 days here at Carneades.org. And stay skeptical, everybody.